Hello, this is Stuart Mason with Math 156 Script 1A. We're going to be using R to solve a small finite probability problem. And so here's the situation. We are given two fair dice, meaning each face has the same probability of showing up as any others. The first one is red, and its faces are 1, 2, 2, 3, 3, and 4. The second is green, and its faces are 1, 3, 4, 5, 6, and 8. And the question is, can these substitute for a pair of standard dice? So in other words, when you roll both these die and sum the outcome, does the probability distribution of numbers match that of a regular pair of dice? And so what we're going to do is create a data frame that has one row for each possible outcome. There are several ways to achieve this. The first is initialize a data frame that has one column named red, which is type numeric, and one column named green, which is type numeric. And then if we see what the outcome of that is, it's just going to be an empty data frame with the column names we wanted, but no information about the actual rows. And the way to give it information is to use this edit function. So we say fundice equals edit fundice, and that's going to pop open this editor, which has columns for red and green, and it's kind of like a spreadsheet. You know, you just sort of go through and you could enter in every red face 6 times, and go through and enter the green faces in order, cycling through 6 times. And if you were to do that for all 36 rows, then you would have a data frame with every possible outcome. Of course, that's a little bit tedious, so we're going to try and find a faster way. Well, we can create each vector independently. So we can say, okay, red is going to be 1 repeated 6 times, 2 repeated 6 times twice, or 12 times, 3 repeated 12 times, and 4 repeated 6 times. And then kind of the opposite situation for green, we're going to take all the possible faces of green and repeat that 6 times. Then all we have to do is call the data frame function on red and green, and that will produce a data frame which has red and green as each of the column names, and the vector values that we specified as the columns. Finally, we can use the expand.grid function that we saw in class. So this is going to compute the Cartesian product, or every possible pairing of the two columns. So let's do that. The only thing about this is it doesn't know that we want to call them red and green, so we take a look at fundice. You see the content is exactly what we specified, but the column names are var1 and var2 by default. So we use this names function to re-specify that red and green are the column names, and then we call head just to see the top and the first 6 rows. Head is a pretty useful function if you're dealing with a nice and long data frame. You see how calling head didn't fill up the console the way it does when I print out the whole thing. Now we can use this $ operator to extract just the green column as a vector, and if we did the same thing with red, we would get just the red outcomes. So now, all we have to do is take funny dice red and funny dice green and add them together and store it in a variable called total. And now, total is, with equal probability, every possible outcome of rolling both dice. And we can use the table function to make a frequency table. And this returns what's called a named vector. So the attributes at the top are the names of the elements, and then the attributes at the bottom are the number of times each of those elements occurred in the vector we tabulated. So this tells us, for example, that 2 is relatively rare and there's only one way to get it. 4 is slightly more common and there are 3 different ways to achieve 4. 7 is the most common because there are 6 ways to achieve it. And then as you go higher and higher, the probabilities tail off symmetrically until we're up to 12 where there's only one way to achieve it. And this should look familiar, especially if we represent this visually. So let's make a bar plot. And sure enough, it's the familiar 2 dice distribution where there's only one way to get 2, a pair of 1s. There are many ways to get 7, and there's only one way to get 12, a pair of 6s. The next thing Paul does is turn this into a probability mass distribution by dividing the frequencies by the total number of outcomes. Now, this works just, actually, what Paul has is 36, because that's the total number of possible outcomes, and I made a slight change to my version of the script by putting the sum of the total options. So I think that's slightly more general, although it achieves the same thing. And if we take a bar plot of mass, sure enough, the shape didn't change, but the y values did, and now instead of raw counts, we have the probabilities of each value. And if you were to add up the probability of each bar, you would achieve 1. So now, let's consider sampling this population, which is equivalent to rolling these die. So our first option is to use the sample function, which will take its first argument, the vector that you want to sample, The second argument is the number of samples you want, and the final argument is whether or not you want to sample with or without replacement. And so since in our situation, when we roll the dice twice, the second outcome can easily be the first outcome again, we're going to say the replacement is true. And so we sample the space, and sort of this is the results, right? You see 2s are relatively rare, 12s are rare, they didn't even show up. We got one 11 and a couple 3s. Oddly, we got no 7s, although I'm sure if we did it again, we'll get a different result, and this one's likely to include 7s. There they are, 2 7s. And then, of course, instead of sampling the total, we can just sample our rolls. So this is equivalent to just rolling a red die, and because it's random, we can do it again and get a different result. Now, it's also possible to sample from the rows of the data frame, but it requires a little bit of clever coding. So if we just pass the data frame, R will randomly return columns. So we're saying sample funny dice 5, and it's going to say, okay, here's 5 random columns from funny dice, which doesn't really make a lot of sense in this application, right? We get green, we get red, we get 2 extra green. Oh, actually, we got 3 extra greens. So there are situations where that's helpful, but obviously that's not going to help us solve our problem. So what we're going to exploit is the fact that R can let us access elements of a data frame much like a matrix. So for example, if we say 14, 0, that's saying row 14, all columns. So this is just going to spit out the 14th row, which happens to be 2 and 3. If we change this to 15, we're going to increment probably red, I think. Yep. Oh, no, green. If we change it to 16, it'll increment green again, etc. Now, we can extract more than one row by passing a vector of indices. So this should return the first, fourth, and sixth rows. And there they are. So this means that if we sample the number of rows and use them as indices, then we can randomly extract rows. So here we have a sample from 1 to 36, asking for 10 random values, and those are the indices we're getting, and if we extract just those rows, now we have a random draw of rolling both die. So here Paul's loop does that again and just puts it in a variable, and we can make a bar plot of the results. Now it looks very different from our ideal bar plot of results, but that's because we have so many small number of samples, right? If we were to sample it more times, we would definitely get something that looks more like the population distribution. And sure enough, we can turn that into a mass function. And then now that it's scaled, instead of getting counts, we actually get something that looks very, very much like the distribution from before. Great. I hope that made sense. Feel free to email any questions to smason@post.harvard.edu, and I'll try to include that email address in the description. Great, and I'll see you guys on Wednesday.